month and a half in hiatus. Well, finally, we are back with our second MLOPS ANZ event. And today, as usual, we have me. My name is Xin Liang. I'm the head of AI at Sales. And we also have Abhinay Katuria, the senior MLOps engineer from REA. And Samuel Tan, also an senior MLOps engineer from carsales.com. And yes, so it's good to be back here. So how are you guys going? Yeah. So Abby, what's going on in your MLOps world?
Yeah, pretty good. Really looking forward to Zin's talk today as well. And yeah, our journey is still continuing. Looking forward to we've moved everything to Metaflow. So
everything.
Exciting.
Wow.
So yeah, it's been a fun ride so far.
Well, it's not just fun, right? I'm very sure there'll be like a issue, things like that. What's your?
Oh yes, we don't talk about that, right?
Yeah.
Talk about what we're talking about now?
Yeah. All right. So yeah. So you know what? This event is not all about us. So I think that's enough for us, like a chit chatting. The main focus for today is actually Xin Liang, and she is she's actually an ML engineer lead at Eliiza. Yeah. So and Sam, you want to bring her in?
Sure.
So everybody can see her.
There you go.
There you go. And Xin Liang is a machine learning engineer lead at Eliiza, like I mentioned earlier, and who has considerable experience in both software engineering and machine learning. And Xin has worked with technologies such as deep learning, computer vision, natural language processing, and signal processing, web product development, and cloud engineering. And with great passion for AI, she's focusing on her using engineering skills to develop, build, deploy, and scale machine learning solutions. And well, welcome, Xin Liang. It's good to have you here. Yeah? And today, it's a very lucky day for us because Xin Liang is going to talk about MLOps, the journey of machine learning at Eliiza. Yeah? And where she's gonna showcase the wider adoption of machine learning in her company and how she actually using the ML platform. Yeah? The one I'm actually very interested to know is this thing called a weights and bias. Yeah? So how she actually use it to actually drive the Eliiza. So without further ado, I'll pass the mic to Xin Liang, and she can start with her presentation. And actually, before.
Thanks, Gus. Could you hear me okay? All right, I take it as a yes, and then I will start. Well, hello, everyone. Thank you for coming, and I am Xin, and I'm also the tour guide today to take you on a journey of a machine learning model, traveling through a system from experiment to production. And we also have a popular term for it, MLOps. First of all, it's a little bit, a bit of a journey of myself in machine learning. As you can see, this is a picture of me in the pre-COVID days, working enthusiastically to teaching my machine to learn and putting model into production. And this is a picture of me on a post-COVID workday doing pretty much the same thing. So I started my machine learning journey as a product engineer graduate in a mining technology company, developing machine learning models to classify operations cycles of heavy mining machines. And then I moved into the startup world as a software engineer, developing image search engine as well as natural language processing speech analytics engine using computer vision and natural language processing techniques that I picked up along the way. Now, I'm spending most of my time trying to figure out how to operationalize machine learning models at scale. Having been enjoying software engineering for a while, I would like to think that machine learning model or machine learning solution is an extension, or machine learning solution development is an extension of a software application development. And putting machine learning models into production, aka MLOps, it is similar to putting a software application into production, what we know DevOps, but not only with code, but also with data and model artifacts. So from DevOps to MLOps. What is MLOps exactly? According to Wikipedia, MLOps is a set of practices that aims to deploy and maintain machine learning models in production reliably and efficiently. The word is a compound of machine learning and the continuous development practice of DevOps in the software field. So you might ask, why MLOps instead of just pure DevOps? Machine learning systems consist of not only code, but also data and models. And machine learning applications include not only deterministic components, that is code, but also non-deterministic components, such as model experiment. And machine learning projects are usually conducted by hybrid teams, including data scientists and engineers. Due to these distinct characteristics of machine learning practice, machine learning requires a unique lifecycle management from data, model, and code to governance, orchestration, deployment, and monitoring. And machine learning system also has a unique workflow from experiment to deployment. It also requires a unique development process to facilitate hybrid teams. Therefore, MLOps is born. And today I'm going to use a natural language processing 101 model, sentiment classifications from IMDb movie review data to illustrate the journeys that a machine learning model will typically travel through the MLOps system. It includes the following steps: experiment, test, release, deployment, and monitor. And our first stop is experiment. Think about when you do software development, you have a function logic in mind and you want to test it. So you write some code and then run it and see whether it works. If it does, then you commit it to a source code repository. Similarly, during model development, we also have to do model training. We train the model with different data features with different model configurations, and then once we train the model, we want to test it and evaluate it and see whether see how it performs when making predictions. And this process is called experiment. And we would like to track all the experiments that we have run on a particular model for specific problems during the development process for auditing and traceability purpose. And therefore, in order to track those experiments, we have a experiment tracking platform as a component in the MLOps systems to track all the experiments that we run, including the trained models, as well as the relevant metadata, as well as the configurations for the model training, and also the data they used to train the model. And here is an illustration of a model training set with experiment tracking. So as you can see, this is code slip of a training function, and there's a Python's decorator here to abstract the general or predefined kind of a tagging scheme. For example, the experiment type and the job type, whether it's a train, whether it's a process a step, or whether it is a evaluation step. And this is a train function, and you can see we set the training configurations and also lock those configurations to the experiment tracking platform. And as you can see, the training metrics during model training are also returned and locked to the experiment tracking platform via a callback function. After the model training finished, we will have a trained model, and we will also like to register the trained model as well as the relevant artifact to the experiment tracking platform into their so-called model registry to store the model with relevant tags and versions. And this is what it looks like on the experiment tracking platform after the model training. So you can see we have the tagging scheme generated, the experiment, and the job type is train, and all the training configurations that we set and registered, and also the training metrics here. One thing I would like to highlight is that, as you can see here, the learning rate and epochs are set as the weight and biases. configurations. As Gus mentioned previously, that there's lots of experiment tracking platforms out there that you could utilize and to kind of like log the metadata and the information during your model experiment. And the one that I use in today in the talk, it is weights and biases. And here it is part of the configuration that I could set and I could assign variables to. And the reason I want to highlight this, it is that these two kind of like configuration set as the weights and biases configurations are for hyperparameter tuning from the weights and biases platform that I will touch on in the next slide. So as part of the model training set, we usually need to kind of like select a set of parameters or model configurations to optimize the model performance, whether it's like the prediction accuracy or kind of like relevant performance measure. And in order to track, in order to select a set of parameters for the model, as well as to log them into the same experiment tracking platform, so that we could trace and audit the experiment that we have run. Weights and biases provided a feature called sweep to exactly serve this purpose. So in order to utilize the weights and biases sweep function for model hyperparameter tuning, it requires a configuration file like the sweep YAML file. It includes the path to the model training scripts to be run for the hyperparameter tuning, and the method of the tuning. For example, Bayesian, grid search, random search, all those like methods that you could choose, with, whichever that is the most suitable one for your hyperparameter tuning exercise. And the metrics to evaluate the model performance, in my case, is to minimize the validation loss of the model. And last but not least, the parameters to be tuned. In my use case, I just use a learning rate and epochs to illustrate, as a basic examples for the parameters to be tuned. And as you can see, I set a few values here for each parameter, and you also could, put a range in for the sweep, the tuning job to kind of like select the values based on your the method that you chose and to do the tuning. To execute the parameter tuning on the experiment tracking platform, in my case, weights and biases, we run a sweep command, which will launch the agent and also start the sweeping job or the hyperparameter tuning job on the weights and biases platform. And what it would do is that it will kind of like start using the parameters that you put in and start doing the tuning jobs. And it also logged all the parameters selected for each experiment run, as well as the metrics that you specify. So yes, you can see on the graph on the right-hand side here, it logged all the parameters for each run, as well as the metrics. So as you can see here, for the validation loss, we have this run that has the lowest validation loss, which corresponds to the learning rate as a 0.00001 and the epochs as 3. And as you can see, based on the metrics, a set of optimal parameters for the model training can be obtained from this hyperparameter tuning based on the metrics, the evaluation metrics predefined for the model tuning. And it is a kind of like put everything together. This is the model experiment system diagram. It includes 3 main steps: data preprocessing, model training, and model evaluation. And each step, we would like to log the information and metadata to the experiment tracking platform. And there's a few kind of like convention or standard that's set up in this diagram. As you can see, this is a tagging mechanism, and also the information, the metadata, as well as the artifacts that usually would get registered to the experiment tracking platform. For data preprocessing, we usually log the input data set reference, whether it is the actual data set or just a reference pointer to the location of the data set. The the output of this step will be the training data set reference as well as the evaluation data set reference. And as part of the artifact, it's always good to kind of log the feature schema from your both the training data set and the evaluation data set, so that we know what features are used for this model training. The next step is model training, and the information and metadata that log from these steps usually are the training configurations, the training data reference, what data is used for this particular experiment run for model training, and then the model training metrics, as well as the output reference. And of course, once we've done the model training, we have the artifact, the trained model that we would like to register as the model artifact in the experiment tracking platform. The third step is model evaluation. In this step, we usually log the evaluation configurations and the evaluation data reference, as well as the evaluation metrics log into the experiment tracking platform. And sometimes during your evaluation process, you will generate some other artifacts, for example, histogram or the area under the curve diagram. So those can also be registered as evaluation artifacts onto the experiment tracking platform. And this is what it looks like on the tracking platform after the experiment process. You can see the text or experiment, and you have all the steps run and logged to the platform, and all the other configurations, as well as the metrics generated from the training as well as the evaluation steps. So once we have done our experiment, found the right model architecture as well as the right set of model configuration, the model will travel to the next step to be tested. And here it is where the model evaluation component needed in the MLOps system. When you do software development, we have unit tests to test the code to make sure that the function, the logics are behaving as expected. Similarly, when doing model development, we would also like to test the trained model and make sure that it performs predictions as expected. And that's when we need the model evaluation in place so that we could evaluate the model before releasing them into production. And this is what it looks like after we conduct the model evaluation steps and log all the information to the experiment tracking platform. As you can see, there's a experiment tag and the evaluation job type and all the configuration, as well as the evaluation metrics as the evaluation accuracy showing here. As part of the model evaluation, we often need to compare different models with different training data, or the different models that are used different set of model configurations, or even different models with different architecture. To choose like the best models from our experiment, and then also tag it for release. So that's what it illustrates here, the 3 steps: compare the models, select the best models, and then to tag the model for release. And so I have 2 scripts here. This one is for selecting the best model, and the other one is to tag the model, just to illustrate what it looks like in code. And essentially, when we select the best model, essentially we just compared different models based on the predefined evaluation metrics. In this case, it's just evaluation accuracy. As you can see that we compare all the models with their we compare the evaluation accuracy from all the models that we have run experiments on and trained through the experiment workflow, and then we will pick the one that with the best evaluation accuracy, and then tag it as the champion model, which is selected for release. So you can see we also tag the model, set a champion tag here. So these two pictures are actually a screenshot from the experiment tracking platform. And here, again, it is to illustrate where the model evaluation sits in the experiment system diagram. So in this kind of experiment workflow, the model evaluation component has been considered, and also the model evaluation metrics are logged from the workflow and to the experiment tracking platform. And these metrics will be evaluated against with a predefined threshold, for example, a accuracy threshold later on, to make sure that the models actually passed the test before release. Once the model has been developed and also quality assured, it reaches the release stage. Think back onto software development when we are going to release a software application. The release pipeline, or we call it the CI, continuous integration pipeline, usually includes these two steps: build and test. For model release, a CI pipeline for a machine learning model usually includes these three steps: build to build the model component, and test to test the code that it's working, and also trained to actually trigger the training pipeline again to generate the latest model artifact. Even though we have done the model training in the experiment workflow and we also have a trained model, it is generally a good practice to trigger the training pipeline again and to generate a latest copy of the model to make sure that it is trained on the latest data, up-to-date data, as well as the latest configuration and code committed to your source control repository, so that to make sure that the model to be deployed, it is up to date. And here is a model release workflow. In the CI pipelines, it has the following steps: build to build the model training component, test to test the model code that is actually working, and then train to actually trigger the model training pipeline. And this is what it looks like for the model training pipeline. The model training pipeline is actually executed on an orchestrated pipeline platform, which it is separated from where the CI pipeline is run. And as you can see, this the training pipelines includes the three steps that are the same occurred in the experiment workflow, including data preprocessing, model training, and model evaluation. So those three steps in the release pipelines are actually run as part of the training pipeline instead of the experiment workflow. And so that's, as I mentioned previously, that's the purpose of that. So after the training pipeline, we will have a updated or up-to-date model for deployment, and to make sure that it is running on the, it is trained on the most up-to-date data as well as the latest configuration and code. So here it is a model release system diagram. We could start from the top right corner here as a CI pipeline, go through the build, test steps, and then trigger the training pipeline on a orchestration platform. In my case, I use Airflow as the pipeline orchestration tool running on the cloud with compute resources, and go through the three steps that I mentioned previously. Similarly to the experiment workflow, we would also like to log every the metadata and the information from each step to the same experiment tracking platform. And the information to be logged is also similar to that from the experiment workflow. A few things I would like to highlight here is that first, the tagging scheme is different. So here we use the release and pipeline tags instead of the experiment tag, so that we could differentiate this. It is a training pipeline versus previously it is experiment workflow. And also all the information and metadata that coming out from each step are logged into one pipeline run. instead of like separate runs. So that indicate that this is one training pipeline run. And the model artifacts generated from the model training set are logged to the experiment tracking platform and also registered into the model registry with proper like, versioning and tags. And these are the artifacts to be deployed into production. And similarly, the model evaluation metrics are also generated and logged to the platform, which will be evaluated against for deployment. And here's what it looks like once you run the training pipeline and log the information into the experiment tracking platform. As you can see, this is the pipeline tag, and all tags and all the information from different steps are logged into one pipeline run. And this is the evaluation metrics, which is the evaluation accuracy from the evaluation step. And you can also see that the model artifacts or the trained models are also logged to the model registry on the platform, and it's with proper versions and tags. And at this stage, it's like still model release. So previously we tagged a selected model as champion, and now we are going into the model. We're in the model release stage. So we'll update the tag to staging, meaning that it is ready for deployment. So after the release stage, the model reaches the deployment step. When deploying software applications into production, the deployment pipeline, or we call the CD, continuous delivery pipeline, usually includes two steps: review and deploy. For a model deployment pipeline, it includes evaluation steps to evaluate whether the model actually meets the criteria, the predefined criteria. The build test steps to actually build and test the model component to be deployed, and then the deploy step to actually deploy the model into a target environment. And here is what a model deployment workflow looks like. So in the CD pipeline, we have a evaluate step to evaluate the model, and then a build step to build and package the model into a deployable component, and then deploy the model into target environment, whether it is a staging environment or a production environment. In the evaluation step, there's either a manual or an automated process happens to actually evaluate the model and see whether it meets the predefined criteria. Usually it is a threshold comparison between the evaluation accuracy as the predefined accuracy threshold. If it passes the test, then it will actually tag the relevant model in the experiment tracking platform with the proper tag and tag it for deployment. As you can see here, the tag is updated to production, meaning it is ready for deployment. In the build step, it will actually retrieve that tagged model from the experiment tracking platform, package it with the code and other configurations into a deployable component, and then deploy it to the target environment. Now let's deep dive into a model deployment component. What it actually looks like inside that component when the model is actually deployed into production. So during the model deployment, what it involves is actually two main steps. First, we build the model and package the model into a container with all the necessary code, artifacts, and configurations. And then when we say deploy it, in my case, I deploy the model as a API endpoint into production for real-time inference. And inside the container, there are three key components, which are inference handler, handler service, and model serving. I use AWS SageMaker Inference Toolkit as a framework to package the model inference code into these three components. And I found that even though it is from this AWS SageMaker suggestion, kind of like a framework, but I found that the design as well as the setup of the framework are pretty well thought out, and I would say that it can be generalized for deployment outside Amazon SageMaker service, as well as a kind of like a generic model inference deployment framework. I think that is a really good practice to have, especially when we want to set up some good standards and good kind of like convention when we do machine learning model deployment. And so let's have a look at these three components. First one is like the inference handler, which does all the heavy lifting for model inference in production. It includes a load model steps to actually load the pre-trained model into memory, and then a pre-processing step to pre-process the input so that it can be model compatible. And then you actually run the model inference on prediction and generate a prediction from the model. And then you format that model output into a desired output. So these are the four kind of like key but also general steps for model inference, and I think this is a good framework to actually abstract those 4 steps, so that you could reuse this, use it as a template, and then reuse it as a framework, in your further model developments in the future. And there's another 2 components. One is a handler service. Essentially, it is a framework to just package the inference handler as a web API endpoint, and then the model serving. Essentially, it is a framework to start the inference web server in production so that it can expose the endpoint to the end user. And here it is the model deployment system diagram to put everything together. We could start from the CD pipeline on the right. So it goes through the evaluation steps and then tag the model for deployment, and then during the build and test step to actually retrieve the model artifact from the experiment tracking platform and package it with the code and configurations into a deployable component, and then deploy it to target environment, whether it's non-prod or prod. And in my case, the model inference deployed into production, it's served as an endpoint for real-time inference. Once the model is deployed into production, that is not the end of the whole journey. There's a really critical component in the MLOps system to actually monitor the model and make sure that it is behaving as expected in production, which is the monitoring component. Again, think about when you do kind of like software application development and deployment, when the application is deployed into production, you usually have like logging and monitoring to make sure that the application is behaving as expected. Similarly, we will have model monitoring in production to make sure that the model or the model that we trained and deploy into production is behaving as expected. And the monitoring components is not just with the code, but also we need to monitor the incoming data to make sure that it's aligned with what we expected during the model training process, as well as the performance, or we call it the accuracy of the model in production. And here it is the model monitoring system diagram. The few things that I want to highlight is that we have a certain information and metadata that we would like to log during the in production for the model monitoring components to make sure that the model and application is behaving as expected. So the first thing, it is the input data distribution. Usually this is corresponding to the monitoring of data drift. We want to make sure that the incoming data is what we expect, what the model is expecting from the during the model training process, so that we understand that this is the set of data that the model can perform prediction accurately on. If there's any kind of distribution shift, then we might have to investigate, see what is going on and what caused that. The second thing is prediction distribution, which adjust the monitoring, which adjust the consent of a concept drift, meaning that whether the model is actually behaving as expected. For example, a particular model would be suitable for a particular problem, but as either the incoming data kind of like evolve or change, and also the problem itself probably is also kind of like evolve or change. So it's not really, the problem that the model can address anymore. Then we would like to know when that happens in production, so that we could take timely and measures accordingly to see whether we need to update the model to make sure that it adjusts the right problems in time. And that's what this prediction distribution monitoring is for, to monitor whether there's a concept shift and whether there's any model updates required. And last but not least, it is the model performance that we want to monitor. And that's probably it is the most important thing, that we want to see whether the model in production is actually producing accurate result and accurate predictions. If not, then we will have to, again, go back to development, go back to experiment to update them. And also notice here that because all the informations are logged to the same experiment tracking platform as the one that's used in the previous steps, so that we would also like to update the tagging scheme to make sure that understand those information belongs to the monitoring component. And here's what it looks like for model monitoring on the experiment tracking platform. As you can see, we have tags, meaning that these are the information from production, job times monitor, and the other kind of like model metadata that logged into here. And as you can see that there's the three columns corresponding to the three key information that I mentioned in the last slide to be logged for model monitoring. First, it is the input data information. In my case, it's the average length of the review or a text, to make sure that that is not out of the scope that the model can handle. And the second thing, it is the prediction, the prediction probability, which it is corresponding to the concept drift. We want to make sure that the prediction probability is within what we expected. And last but not least is again the prediction accuracy, to make sure that the model performs in production is actually generating accurate prediction. So that's what it looks like for model monitoring on the experiment tracking platform. So to put all the steps and all the components all together into one diagram, and this it is the system diagram of a machine learning model journey. We start from the left-hand side here. It is going through the experiment and development stage, and we have, which will produce a right model architectural approach and relevant configuration, and then it goes to the CI pipeline for model release, and trigger the training pipeline on the orchestration platform and updated the model to be deployed. And then during the CD pipeline, we will retrieve that trained model from the experiment tracking platform, performs a last gatekeeper evaluation to make sure that it meets the criteria, and then we package it into deployable component and then deploy it into target environment, if it's prod or non-prod. And last but not least, we will also need to implement a monitoring component in production to make sure that the model in production is behaving as expected. On the occasion of a performance degradation in production, we could either trigger the model training pipeline again to train the model with more up-to-date data or updated configurations, and then to update the model, and then it will go through the release and deployment workflow again to be deployed to production. If there's if that cannot address some other problems that we observed or monitored in production, then we might have to go back all the way back to the experiment and development stage and to do further investigation and see whether there's a model architecture need to be changed, or whether we are actually solving the right problems in production, so that we might have to do some experiments, development, and investigations again, so that we could generate a more appropriate model for the problem we want to solve in production, and then go through the whole journey again. So this is the overview of a machine learning model traveling through the journey of a machine learning model traveling through the whole MLOps system from experiment to production. There are a few takeaways that I would like to highlight here. A machine learning system consists of experiment tracking, pipeline orchestration for model development, automated pipelines for model deployment, and model monitoring in production. The journey of a machine learning model from experiment to production is an essence of the MLOps. And MLOps is a set of practices, includes establishment of technical components, as well as the process and workflow of the machine learning lifecycle. So it's not just the technical components, but also the workflow and the process that you put on top of it, and how the different teams work together to follow the process with the best practice to create the whole MLOps ecosystem, if you will. And the complete journey of a machine learning model, it is a result of not just a good MLOps system, but also a cultivated culture in the machine learning practice, including the process and the workflow with best practice that I mentioned previously. And that is pretty much what I would like to share with you all today. Thank you for joining, and thank you for sharing this time with me.
Cool. Thanks a lot, Xin Liang. That's an awesome talk. Wow, it's full of details, and I'm very sure that will be very beneficial to all the audience, not just us, the host here. And yeah, so now we are entering the Q&A section. It's gonna be a casual Q&A, we all chatting, and I'm very sure Abby and Sam and myself, we have plenty of questions, but we're also gonna raise questions from the audience. There are a few that already been logged there, and we're gonna bring it up here for you to answer. And the first question actually from Fauzi Akbar, and he asked that, well, thanks for the informative presentation, and he was wondering if what is the cloud architecture supporting this pipeline? Like you mentioned weight and bias, right? But behind the scene, is there they fully manage the architecture, like the cloud infrastructure? Oh, so yeah. So if you want to take on this question,
yeah, sure thing. Maybe if I guess I'm not sharing my slide, but that's okay. So I think to answer that question, I think the cloud architecture to support the pipeline, all the components that I mentioned on the slides, they are built on AWS. Apart from the weight and biases. So what happened is that including the experiment and the development workflow, and also the training pipeline, as well as the prediction services and monitoring components, they are executed and run on AWS with different cloud services or infrastructure. And I mentioned one is Airflow. That's what I use. I use the managed Airflow on AWS to set it up there. And then for prediction services, I mentioned SageMaker, which it is I utilize the AWS service and deployed the model there, as well as using their training infrastructure. But for the experiment tracking platform, which is the weights and biases, that is a third-party managed service that I just utilize their offering. Essentially, it's their framework, Python library, but I use the platform that they managed. So essentially, I just log the metadata information and also artifacts over to their platform, and they managed it. I hope that answers the question.
I see. So when you actually conduct when you train the model during experimentation, it was like a train within the weight and bias. It deployed to cluster behind the scene, or actually no, you actually deployed your own cloud. You're just basically using weight and bias to track. Yeah?
Yes, the latter. So the training, the component is actually a SageMaker training job, like we package the code, the model, and then deploy it and to do the training. But inside the training code, also utilize the weight and biases library so that I could log. And I also create a framework, experiment tracking framework, and which is built on top of the weight and biases API, so that I could track the information and track the and also register the artifacts to the weight and biases platform. So as you say, Gus, that the weight and biases platform, it is for tracking and consolidate and capturing all the information together.
Oh, so that I saw the code utils.log model. It's actually weight and biases framework, or actually.
The util.log model. Oh, that is okay. So that is the experiment tracking framework layer that I put on top of the experiment, on top of the weight and biases API, so that I could put some conventions, put some kind of like tagging and versioning scheme on top of it.
Cool. Wow, cool. So totally understand it now, more clear. Thanks a lot. So yeah, I'll pass it to Abby or Sam. Do you have any question?
Yep, I can go next. Really, first of all, really great talk. Learned heaps. So thanks for that. In the presentation, you talked about model inference from a live API side of things. How does batch inference look like for you, or do you have a use case where you use batch inference?
Yes, that's a great question. So as I mentioned, that my use case is actually for a real-time inference, and to be honest, the batch inference probably can actually be a bit more straightforward than the real-time. And what we kind of try to achieve is more like a batch and real-time kind of like a model uniform, like to unify those two kind of practice together as much as we can from a model MLOps system perspective, and only need to change the last layer of the configuration, whether that model needs to be served as a real-time endpoint or run as a batch job. So essentially, in the practice, what we could do is that, and what I also did is that we packaged the model into the container, and that is the kind of a deployable container with all the model inference code inside, and then that can be used for both a batch and real time. And then we will just put another layer at the end of that container to say, okay, so let's expose this container. We can configure it, expose this model instance or model container as an real-time endpoint, or you just need to run it as a batch job, just a command to say, okay, run, literally just like run this container batch, and then we just run as a batch job, so that we could. So in that case, we could kind of unify all the components for different use cases as much as possible. By different use cases, I mean batch or real time, so that we could mainly for reusability, so that we could reuse this kind of like a framework, this kind of platform for different use cases in the future.
Great. Yeah, that answers my questions. Thank you.
I got a question here lining up from Dean Bud. I'll just bring it up here. What do you use to detect drift when monitoring your models? And do you use something like TensorFlow, data validation, or custom algorithm? Yeah.
Yeah, this is a great question. And in terms of detecting the drift, I have to say that often from my experience, because each model solved specific problems, and for each specific problems, they require a different kind of like characteristics, or almost like a different kind of characteristics. Yeah, that's a good word for like from the training data. So it is a really kind of like custom and specific thing for each different model. So in terms of detecting the drift, let's say for data drift and also concept drift, usually we the thing that I mentioned here, we use something a library called Evidently. And what it provides a framework to perform all this like the drifting tests, or kind of in the both for the data distribution drift test, as well as the concept or the prediction distribution drift test. But we found that there's a lot packed into kind of like this framework. So what we did eventually is that we probably need to kind of take some out, just like reference to their framework, and see how they do it from a probably a design point of view, and the actual test actually monitor the data drift. We probably have to write our own custom algorithm. And what we usually do is that we kind of we get the set of kind of distribution from the training data set, and we call it as a baseline set for benchmarking purpose, and which can be used to benchmark and compared with the real-time incoming data in production, and similarly for the more prediction distribution as well. So we didn't use the TensorFlow data validation for that, but I did previously a little while ago to use that to actually check, do the basic check with this null, whether there's some basic check stuff that I previously used that. But for this one, I think it's a bit of a customized algorithm as well as a reference to some existing open source framework. Hope that answers the question.
I do have an expansion to that question. This is my own question. Still in the monitoring drift kind of thinking. When you were showcasing the weight and bias, the dashboard where you put in your champion, those tags, I was wondering, is there a timestamp to the model that you're looking at? So I know there's like this model belongs to this version. Is there an indication that when you look at that model, it is of how fresh it is? Can you speak into that a bit more?
Yeah, sure. So in weight and bias, they have this space called model registry. Essentially, it just shifted the focus to the model itself. So you have this model name, and then you have the versions and all the metadata that associate to it. But the key things usually is how actually in my code that I could retrieve that model. It is through something called a run ID. So that in the model for each version, it has a run ID attached to it, meaning that it indicates which run this model is generated from, so that when we go back to the run ID, that has everything of the all the metadata and the information of that run and of the generation of that model, including timestamps and all the other configurations. So the linking between the timestamp and the particular version of the model is through the run ID.
Right.
All the
way up to your inference point. So when whichever front end that uses your inference would refer to the run ID as their go-to guide, just in case like my result is X, which one is the one responsible for it?
Yeah. So we would tag the model, which one is actually for that particular problem, which we would tag the model, which model is actually in production, and then we would tag that into in experiment tracking platform. And also, if sometimes we also do, if we want to see it in code as well, it's probably also worth to have like a model configuration in code in the code repository to illustrate the versions and mainly the versions and the name. And probably for the run ID, but you could retrieve that from the experiment tracking platform, so that the lineage is there to the code and to the experiment tracking platform, and also the actual artifacts deployed onto the in production. So it's all linked back. But yeah, I would say the run ID, that would be a key linking point.
Okay.
So if the model, something goes wrong with the model, spitting out wrong prediction, so you know who cooked the model, right? Like in a restaurant. Some restaurant actually the dish actually come with like name card. Who's the chef who cooked that?
So that's all linked back, so that you know who to blame.
Who to fix it? Maybe just a nice.
Who to fix it? Yeah. Thinking positively, 100%.
Ownership.
We are proud of our work, so yes.
Cool. So wow. So like a lot of questions here. So the next question is from Harshad. He asked, what do you think of the usability of off-the-shelf end-to-end packages like PyCaret? I've seen this library a few times, and that's the majority of MLOps steps, including. I don't understand the end part of the question. Does majority of MLOps steps including till deployment? If you're using Airflow from there on point onwards. So it's 2 questions. Okay. Yeah.
Okay, so it's let me unpack the questions a little bit. So what do you think about usability of off-the-shelf end-to-end packages like PyCarrot?
Yep.
That does the majority of the MLOps steps, including
the end-to-end deployment using Airflow. Yeah. First
so
of all,
it is end-to-end MLOps steps until the deployment
until the
steps,
deployment.
maybe
Yes.
until the deployment steps.
Yeah.
I got asked this question a lot, to be honest. Like, it's kind of like, you build or your own, you use some of the off-the-shelf services for each component, and then you put them together like Lego blocks, versus like you just get it out of box Lego by house or something. I guess it really depends on the use case. I have to say that I'm not familiar with PyCarrot, so I can't really comment on that too much. But I do understand there's like offering, to actually have an out-of-the-box kind of end-to-end MLOps systems. It really depends. Some of the the out-of-the-shelf like end-to-end package that might already suit your needs. Maybe your kind of like ML practice is relatively standard or relatively uniform, so that you don't have like different use cases. You don't need the flexibility. You just want to the standard, just want with the conventions, everything just lift and shift. And for those kind of like end-to-end might be good, so that you don't need to build it. You don't need to come up. You don't need to engineer your own, build your own system. You just use them, and perfectly fine for your use cases. And from my experience, I often experience machine learning practice and use cases that are a bit of a varieties. So like from batch and inference, and also when you deal with the data like structured and unstructured, and then for each one it's a whole spectrum of like machine learning, from a traditional machine learning practice all the way to deep learning, but more like advanced and complex system. So in that case, with the variety, and I think, and also with the it depends on the team. If like the flexibility is something that they would like, I would say that's probably kind of like building a bit more taking a bit more modularization approach, like to package the component together and then build your own that it actually suits your use cases, and also keep it nimble, and also like make sure that it is flexible enough that it set up the good foundations, but allow the scalability. I think in that end, I found build your own with existing kind of like component. With existing services as a component to build your own, that might be more suitable. So really depends on the use case, I suppose.
Yeah, cool. Thanks for the answer. And still around this, I have also follow-up question, actually coming from my own, but yeah, still relevant. You mentioned that you use SageMaker, right, for the deployment, of the endpoint, right?
Yeah.
So then obviously you will actually build your custom container with SageMaker, right? And you deploy that. So is there any CI/CD actually integrated in to deploy this custom container? So just in case if you modify the code, that actually part of the algorithm, it auto deploy. Is that how it works there?
Yeah. So I use to answer the question goes is that yes, I use the inference toolkit and to kind of like package or wrap around the custom model, and so that's in the repo, and also have used the infrastructure as code for AWS CDK to kind of like write out the SageMaker model instance, and also the endpoint configuration as well the endpoint as part of the CDK in infrastructure as code, so that they can be deployed automatically through CI/CD into one cloud stack. So that and during the CI/CD pipeline, there's a step to actually the build step to actually build the container from the repository, and then push it to the container registry, and then in the deployment step to kind of pull that image down and then deploy it into production. So that is all through CI/CD with infrastructure as code, and it is automatically deployed when you kind of like do an update in the code and push it.
So when you do update on the code that is part of the algorithm for the custom container. Yeah, it's not like I know that you're running a continuous training. Yeah.
Yeah.
So like
Yeah.
like if you have continuous training pipeline running every day, so every day you do not really rebuild this container, right? You don't, right?
So that is the step. So as I mentioned, I have two pipelines. One is release and one is like deployed. And it is, and also what I did is actually I set a flag, a trigger, or a switch, if you will, in the CI/CD, because I use GitLab, so that I use the GitLab run configuration. So I actually indicate whether for this push I would like to trigger the training pipeline or not. So I have a switch there. So that if I keep the switch on, that means yes, every commit go through the model training as well as a deployment, but I could turn it off so that I don't need to go through the model training and to kind of like, if it's just for like not for model relevant code changes, if just a typo or something, then it doesn't make sense to trigger the model training again. So I have a switch there.
Cool, thank you.
I hope that answers your question.
Yes, definitely. I'll leave others to ask.
Not a follow-up question, but from Owen Z. Thanks for sharing. May I ask how the platform addresses dataset imbalance during training time? For example, negative sample, overwhelming positive samples.
Yeah. So good question. I guess this question probably is a little bit outside the scope of a kind of like the infrastructure, the MLOps system, but more towards the actual algorithm, the model development. So I guess in this platform, there's no kind of out of the box features to actually address that problem. It is more like when you kind of perform the model training during the pipeline, when you write your own model training code, and also the data processing. So the data processing steps and model training code. In those two steps, you probably have to, if there's a data imbalance problem that in your specific problem that you want to solve, I think that is where it needs to be addressed in either the processing data, whether you want oversampling or undersampling using existing open source library to adjust that, or in your model training code that you want to kind of do a little bit of like a weighting mechanism in the model training. It depends on the model as well. So that will be addressed in those two components or steps, but not necessarily as part of the platform, if that makes sense.
Cool.
Hope that answers the question.
Yeah. I think we have, we don't want to keep you for too long, Xin Liang, but we have one slot for one last question. Yeah. Let me see, is there anybody else asking in?
Sure thing.
Oh, same person, Harshad. He's a very curious person. He asked, this is more like a strategic question than MLOps, but I'll get you to answer this. So,
Sure.
Are you focusing more on data-driven or model-driven? And do you face issue when trying to convey the value of the stakeholder from of one over the other? Is this something that you can answer, Xin Liang? Yeah.
Let me make sure that I understand the question. So do you focus more on being data-driven or model-driven? And do you face issues conveying the value to stakeholders of one over other approach? Right. Good question. This is a great question. I might need to. Okay, so maybe if I understand it correctly, data-driven meaning that you probably focus a little bit more on the work and on the data. So that is make sure that how do I put this? So like your analysis and your insights are extracted more around the data. For example, just use something that some approach that is relatively straightforward that can be explained.
I think the way I interpret this actually, Xin Liang, because it's actually a popular topic that recently Andrew and G mentioned that in order to improve your AI model accuracy, you can either spend weeks trying to improve the model architecture, or you spend just a couple of days or some weeks on improving the data quality, or the data quantity. Yes.
Yeah.
So which approach actually
gotcha.
you take on this?
Yeah. Okay. Yeah. So thanks, Gus, for explaining that.
No worries.
Yeah. Okay. Okay. So that is a good question. Oh, this is a hard one. It really depends. So I have come across okay, so put it that way. I think if we can get more data, I think probably a bit more data driven, it might seem to be a bit more straightforward sometimes. If you have the luxury to get more add to the variety of the data. I deal with like image a lot, so I do image like augmentations, like lighting and skewing and rotation, and you could augment the data to create a variety as well as increasing the quality of the data. If that is a relatively easier way to do, then I would say go with the one that would work, and also it is more straightforward. But I also have encountered a time that I wasn't able to get the quality of the data. We just only have that much data and with that much variety, so we have to be creative on the model end, whether it's like we kind of increase the complexity of the model architecture, or we have to have an ensemble model to adjust like different considerations as like a sub models to solve a particular intermediate problems, and then merge them together to boost the accuracy of the whole model system. I think I would say it is a use case by use cases. It depends, but I would say usually my understanding is that usually the data-driven approach it is a bit more straightforward if you can. But I have seen both, so yeah, it depends.
Cool. Thanks a lot for that. Yeah, you can say that actually, if it doesn't matter how good your learning capabilities, if you're learning from the wrong data,
Yeah.
you'll end up with the wrong result.
Also, if you are learning from the wrong data or irrelevant data, then it's probably difficult.
As we say, right? Garbage in, garbage out. So that's basically it.
But you can think of it. Maybe I'm just in my perspective. I'm thinking while you guys talking is, if the problem lies with the data, then you focus on the data. If the problem lies with the model, you focus on that. If you don't know where the problem is, that's where your difficulty is. Which one do you focus on? I'm guessing this way it's not one or the other. It's like you do data driven because you have a good quality data, you work on it more, or your data is bad, you don't have the capability to work on it. Therefore, you go around the other end. So is that how I'm seeing it? Yeah.
Yeah, it did. Yeah, that's a good point. Kind of like chicken and egg, like chicken. But I guess where I was thinking as kind of like a step ahead, that provided that we understand the problems, we know this is like the right approach overall, like and then we know that that's the data that we need. We just like I would just like answering based on the assumption that those all elements are all aligned and we understand what we're doing, and then but it's just like it's the next level in terms of like it is the restriction that we can't it's a kind of like a limitation that we have to work around, and that's the approach. But 100% like step back, probably need to make sure that we understand the problem, choose the right approach, and from the model perspective and also from a data perspective. But I totally agree with both Chris and Sam. Excuse me.
Awesome. So that's a full-on session. We only have one speaker, but I think we take a lot from your brain, Xin Liang, which is awesome. And I hope that actually, I learned a lot today, and I'm hoping that everyone here plus all the audience also think likewise. Yeah. And so thanks for joining us, Xin Liang, and I really appreciate your time and your effort in presenting your journey, for the benefit of everybody's learning. Yeah.
Thank you for having me. I really enjoyed it.
No worries. And with that, that's the end of the session. But before we all disappear, we just want to actually let you know that we will have another session probably after the Christmas break. Yeah, we'll have a peace and quiet Christmas. And if any one of you keen to share your experience and journey, please do so. Reach us to me, Sam, or Abby. Yeah? And like I said, this is like the platform for us to share and learn together. Yeah? So the more you share, the more you benefit the rest of the community, and we all improve together. It's not a zero-sum game. Yeah. So whatever we pour, we will come back to us. Yeah. So until next year. So enjoy everyone, and thanks for watching today. Bye.
Okay,
See ya.
here.